It's good that you're still around, because in this lecture we can discuss climate feedback mechanisms. This lecture has 3 parts: an introduction, then we talk about key climate feedback mechanisms, and there's a last part which features aerosols. So in part A, I introduce you to different types of climate variability. We talk about equilibrium states and transitions and runaway effects, talk about climate parameters, and the definition of what is a climate feedback mechanism. What are positive and what are negative feedback loops? Okay, and key climate feedback mechanisms are the water vapor feedback, ice albedo feedback, cloud feedbacks, and the solubility feedback, and some other feedback mechanisms. Okay? So trying to understand what causes climate feedbacks and what is a climate feedback. Okay, so let's get started. Okay. Introduction. Okay, we look at surface temperature changes, for example. Okay, or we look at CO2 concentration changes over time. Okay. And we look at different scales and just grab parts of the data and we look at it. And we can see different types of variability. I just want to introduce you to these different types of variability. For instance, you can have periodic changes, shown here in this graph on the left, which looks like a wave, a sinusoidal wave. Okay? Sometimes it's low, sometimes it's high. So like we had with the ice age cycles, okay, we have that periodic changes. There are several of them. Okay? On the other hand, you might see a step change, shown here in the middle diagram, okay, where you go from a low value and then you get a jump to a high value. Okay. Superimposed are some other modes of variability, higher frequency stuff here that you can see here too. Okay. What you also can see is, you can see if you grab a particular time interval, you might see something that we call a trend. A trend is a positive or negative change. And this trend shown here in this third figure is a positive trend. Has some periodic variability in it too, but it's a positive trend. Okay, and here already comes my criticism, because you actually get a positive trend if you just go back to the first image and you just grab one part. Here you get a positive trend on this on this upward side of your wave, or you get a negative trend on the other side. So the use of the word trend can be misleading, okay? Because by trend you somehow think that it will be continuing into the future, and it always has existed in the past, which is not the case if you look at the periodic variability. So you have to be very careful in the interpretation of figures which show a trend, or in the interpretation of such trends. The fourth example here, shown over my head, is a variability change. So where you have some type of higher frequency variability and then you get a change. Okay, so this is what you also can see, is something happening which causes this variability change. Okay, so these are different types of climate variability. Okay? So now we can have different situations, transitions and stuff like that. And the starting point for that is to look at climate equilibrium cases. So a climate equilibrium is the theoretical case in which the climate system maintains a constant emission temperature. Okay, this is sort of shown here in this first graph where you have a climate disturbance, but it bounces back and you stay in the same equilibrium state. Okay? So similar to what happened after the end of the last ice age. We had relatively stable surface temperatures for tens of thousands of years. Okay? All right. So, however, the climate system has multiple possible climate equilibrium states. Okay? Disturbances can lead to the transition from one state to another. Like the most extreme transitions are between hothouse and coldhouse climates. Okay, so this is shown in this sketch where you have two equilibrium states, one shown in blue and one in red, and you have a transition from one to another state. The mechanisms that trigger the transition from one equilibrium state to another are called runaway effects or positive climate feedback loops. Okay, so here you learn the term runaway effect. Okay, so it's important to understand this concept of multiple equilibrium states. And just for completeness, it's the Planck adjustment that actually stabilizes the climate around these equilibrium states. Okay, it's also the Planck mechanism that allows for the existence of different equilibrium states. All right, so just in general, is what do we mean by climate variables? We mean any physical, chemical, biological, or geological property that influences climate. There's some examples here: albedo, insolation, greenhouse gases, surface vegetation, cloud and ice properties, aerosols, stuff like that. The effects of these climate variables or changes in these climate variables can be expressed as heat flux anomalies in watts per square meters, also called radiative forcing. So you have to imagine that you can, although you have very different processes, you can all express them as a radiative forcing in terms of a heat flux anomaly. And I show you one example what is meant by that. Okay, show you one example here in the next graph, which looks at climate changes between 1750 and 2005. And this is taken from an IPCC report of the Intergovernmental Panel of Climate Change. And you can see that there are different climate variables like CO2. Okay, here's methane, nitrous oxide. You can see references of ozone. You can see references to water vapor, to albedo, to aerosol, to solar irradiance. This is the solar radiation. All expressed on the same graph and expressed by the same unit of watts per square meter as a change in radiative forcing. This is how you can express all different type of climate variables. Okay? And just before we finish off this first part, I just want to mention, while we have this graph here in view, I just want to put an emphasis on why there is often such a focus on CO2, okay, as a dominant effect. It is not a dominant effect. You can see here that the CO2 effect, while the other greenhouse gases have a big effect too, okay, so maybe a little bit more than half of the CO2, but you also have these other balancing effects linked to aerosols. And balancing effects are actually referred to the albedo effect. You know, you learned about the albedo effect. However, if you look at the sum of all these contributions that you have, is that the net effect, the residual effect, if you add all the terms together, ends up to be very similar to actually the CO2 effect. You see, it has the same type of, has the same magnitude. You know, here it's about 1.6 or 1.7 watts per square meter. Okay? All right, so that is something to take away. Okay, and this is why you can use the CO2 effect as a proxy of the total effect. All right, so this is the end of the first part of this lecture.